So the final thing I want to do on these videos is actually just spend a little bit more time with these electron configurations, because these will be really important as we start discussing how atoms or why atoms have the types of properties they do. Remember, I said all chemistry is based on electrons, and is pretty much based, the properties for any particular element is because of their electron configuration. So knowing them is important. So if we looking at this, we have a series of electrons where we have this is a series of electrons in order of increasing numbers of electrons. So lithium's got 3, beryllium's got 4, boron's got 5, and so on and so forth. So the electron configuration and the orbital diagrams are shown here. So lithium is 1s2, 2s2, right? So that's where the electrons are at the lowest energy, and they are not violating Pauli's exclusion principle, and all of the spins are being maximized, which doesn't really apply until we start getting to the p orbitals, okay? So these are the electron configurations, but you notice once you start getting up to sodium, these electron configurations getting rather long. And so there's a way to actually abbreviate these electron configurations, and what you do is you basically use the noble gas. So the noble gas that is the one before whatever electron you're showing the whatever atom or element you're showing the electron configuration for, and add all of the rest of the remaining electrons on top of that. So, for instance, so full N1 subshell abbreviated using noble gas core helium. Okay. So all of these atoms here have this subshell right here, which is identical to the helium subshell. Okay, so they have a full one subshell, so we can abbreviate lithium as helium 2s1. Of course, we didn't really save a lot of space with this one, but we could do down here, this would be helium 2s2 for beryllium. Okay? So helium 2s2, this would be helium 2s2 2p2. Well, the cool thing is we can actually do this for with other noble gases also. If you look at this right here, okay, this entire electron configuration, that is just the electron configuration for neon. Okay, so if you wrote the electron configuration for neon, it would look identical to what I just circled here. And so instead of writing this entire thing for sodium, what we do is we say, well, it's got the electron configuration for neon, plus it has a 3s1 electron, or it's got electrons shown here. And so this is a way to actually make abbreviated electron configurations. Very, very good idea to practice this, because otherwise you'll be writing some of the elements that have a whole lot of electrons. These electron configurations will just get extraordinarily extraordinarily. You can also do the same type of thing with the orbital diagrams. Okay, so right here I have the abbreviation here. So I can, for the orbital diagram, I can say neon, then the 3s up. So this is basically the same thing I have here for the orbital diagram, except this this entire thing here is abbreviated with just in brackets neon, and then I just have this last box here with the 3s. So abbreviated or condensed electron configurations and orbital diagrams are of huge benefit. If this sort of understanding of electron configurations was around when they were first putting together the periodic table, the periodic table might have ended up looking something more along this lines. And notice what this is this is in order. These rows are pretty much in order of how you fill the fill up electrons from the ground state up. You can do the 1s, 1s, 2s, 2s, 2p, all the way through 3s, 3p, 4s, 3d, and so on and so forth. And so this is actually, I'm going to, of course you have this video, so make sure that you spend a little time looking at this, realizing this is the order that electrons are actually filled in. And so if we use the periodic table, instead of having that periodic table for test, you'll actually have this one. So just remember that we go 1s, 1s, 2s right here. This would be 2p. Okay, so this is, or think of this as the p block, 3s, 3p, and so on and so forth. So to use the periodic table to write the electron configuration for bismuth, well, we go down here. Bismuth is right here. We would say xenon is the noble gas core. So we would put in the abbreviated electron configuration. The abbreviated electron configuration for xenon. So that's just xenon, right? In brackets. And then we start doing this. We do 6s2. We have to go down to the F row, so 4F14. Bring the arrow back up to the 5D, 5D10, and then 6P3. So what you'll notice is that once you start adding F rows, once you start getting down into row 6, that's what that little thing on the periodic table indicates. And the F, the principal quantum number for your S or F orbitals, is always 2 fewer than the principal quantum number for S and P. And the principal quantum number for the D orbital is always 1 fewer than the principal quantum number for S and P. Finally, there are a couple exceptions to this order of filling. And you find these in the transition metals themselves. So these 5 transition metals have these weird electron configurations where they have the 3D subshell filled or half filled and the 4s half filled. So instead of filling up the 4s first, so it'd be 4s2 3d4. See, 4s2 3d1 2 3 4. What it does is it borrows one of the electrons from the s subshell and puts it in the 3d subshell. This is because of an energy difference, because this essentially, the configuration lowers the energy, because whenever you have a half-filled subshell or where D has 5 orbitals, right? And so you get 10 electrons total in the D subshell. So since there are 10 electrons total in the D subshell, if you half fill it, you get a decrease of energy. And so what we have here is half filled S subshell and a half filled D subshell instead of a fully filled S subshell and a not half filled D subshell. Okay? So instead of being 4s2 4d or 3d4, which is what we would expect, we find the 4s2 3d5. Again, over here, what we did is we went to a half-filled 4s subshell so that we could fully fill that d subshell. And this happens for copper for Cu, Ag, and Au, and Cr and Mo. So chromium, molybdenum, copper, silver, and gold.